promised, we're going to take a look at a definite integral in this problem. So I want to do the integral from 0 to root pi of 2x times sine x squared dx. And this is a function that, at least on this interval, is never negative. And so it corresponds to the area here between the curve and the x-axis. I do not expect you to know off the top of your head that that's what the graph looks like. I used Desmos before I made this video. I typed it in, I said, oh, that's what it looks like, and then I put it up on the whiteboard. But because this does mean, have a geometric meaning, I thought it would be nice to have a picture of that. Okay. But you'll notice that I've got, again, a product of two functions. I've got 2x being multiplied by sine of x squared. One of those pieces, sine of x squared, is a composition. I'm taking x squared and plugging it into the sine function. The other factor is the derivative of the inside part, because my inside part would be x squared. So the derivative of x squared is 2x. Fabulous. Okay. So if I try to go about doing a u sub, I just give a name to that inside part. So I'm going to say u is x squared. I know this is only going to work if I have a u prime hanging around, because I need that u prime to get absorbed into my du. So while this is new, I usually take the time to actually write out u prime. As I get more comfortable with it, I'll usually go right to just writing that du is going to be 2x dx. And I promise we will come back and take a closer look at what that actually means as we're thinking about this integral. But let's work through it first. So I'm going to now rewrite this in terms of u. And I'm going to make a mistake. So I would like you to see if you can catch me, okay? I'm going to say, all right, we're integrating. Now the 2x and the dx, that's going to become a du. This is going to become a sine u, and we were going from 0 to root pi. Now, I have just made a mistake. I want you to see if you can catch me. Pause the video if you need to and think about it for a little while, then tune back in. Welcome back. Okay. Don't know if you figured it out or not, but the idea is everything that was an x value has to switch to become a u value right now. Now, it was kind of obvious that this and this and this dealt with x's. It was a little less obvious, perhaps, that those were also x values. But here, this would be my x-axis. My lower limit of integration is my starting x value. My upper limit of integration is my ending x value. So these were x values. They're going to have to change. Now, if I want, I can write that I'm going to change to the u value I get when x is 0 and the u value that I get when x is pi, because u is actually a function of x. I think it's simpler to actually calculate what those are. The u value at 0 is going to be 0 squared, so that actually stays as 0. The u value at root pi is root pi squared, so that becomes pi, and then we get sine u du. Okay. Now, you got to change those limits of integration, and it always has to match. If I have a dx here, these are x values. If I have a du here, these have to be u values. I don't care if you've calculated what they are or if you've written that they're the u values I get for those x values, but you gotta have it matching, okay? A lot of times people will come here and then the next step they're like, oh yeah, I gotta change the limits, and they'll change it here. Their work is then wrong. It's gotta always be consistent, always match. Now, what's nice is we can see a picture of what's happening. If I were to draw the u-axis here, okay, I know what my sine function looks like. My sine function, let's see, if this was root pi, and that's about 1.7-ish, so pi is going to be a little bit further along, but the sine function only goes up to a height of 1. Okay. So this integral is representing this area right here. These both areas both happen to be just geometric area because my function is non-negative on the interval. This integral represents this area, but I'm saying that they're exactly the same. Now, when I change the integrand, I'm changing the height function. Over here, I had this function whose tallest point was higher than 2. When I'm integrating sine, the highest point is only 1. I've got a shorter function. if I decrease the height, but I want the area to be the same, I'm going to have to expand the base. So the interval changes to take into account, it's like I'm taking this area and I'm morphing it into something that has a different height, but if I want the area to be the same, it's got to have a different base as well. Sometimes that's going to mean I have a longer base, sometimes it's going to mean I have a shorter base, but if I want to preserve the area and I'm going to change the height, I better change the base as well. Okay, so now I can go ahead and find myself an antiderivative. So an antiderivative of sine would be negative cosine of u, evaluated between pi and 0. Now, since these are u values, I don't need to, in this case, go back to x, because I'm not going to have any variables in my answer. If I have a definite integral, I'm going to be plugging in the limits of integration. And as long as I'm plugging in u values for u, or x values for x, I'm good to go. So this is negative cosine of pi minus a negative cosine of 0. That's going to be the opposite of negative 1 plus 1. That's 1 plus 1. That's going to give me a 2. Now, if I preferred to, I could have gone back to x's. So I could have said that's going to be negative cosine of x. U was x squared. If I go back to x's here, I'd have to go back to x's here. So then that would become root pi and 0. I think that's just a lot more work because I've already done the squaring. Now I've got to do the squaring again to say this is going to be negative cosine of pi minus negative cosine of 0, which is going to be 1 plus 1, which is going to be 2. So either one works. But if you're doing an indefinite integral where the variable is part of your answer, it's necessary that you switch back to the original variable. If you're doing a definite integral where your answer is a number, all that matters is that it matches. Plug in u for u, or x for x, or t for t. Just make sure you're not plugging in u for x or x for u. Okay, excellent. So that's an extra thing to keep in mind if you're doing a definite integral, that those limits of integration have to change. And it really does make sense from a geometric perspective what's going on. Okay. Want to now talk a little bit more about this formula where du we're saying is 2x dx. I think it makes a little bit more sense to talk about this in the context of a definite integral, because this came to us from the limit of a Riemann sum. So if I were creating a Riemann sum over here, I would have chopped this up into little pieces and the base of, and created some rectangles, and the base of each piece would be a delta x. And then when I take the limit of that, that becomes a dx. So it really is coming from a small change in x. Here, if I did a Riemann sum, I'd be chopping things up into pieces, but the base of each piece would be a small change in u. And then when I take the limit of that, that delta u becomes a du. And if you think back, we did study the meaning of differentials by themselves as well. So here we had u was equal to x squared. Okay. So this would be like x, and u is a function of x. Now, I can talk about what those differentials mean. Because if you remember, we said dx and du were actually variables that represented a small change in x and u respectively. Essentially, dx corresponded to the run of my tangent line. Whoops, I should have drawn in a tangent line here, shouldn't I? Yes, I should have. And du was the rise of my tangent line. Okay. So in a Riemann sum, I would have a delta x and a delta u. Once I integrate, that becomes a dx and a du, but they really are corresponding to the base of those rectangles, a small change in x or a small change in u, and there's a relationship between those, because I know that rise is equal to slope times run. So when we studied differentials, we had this relationship that du was actually a multiple of dx, and not necessarily a constant multiple, because if x is changing, then this factor of 2x would also change, but the rise is always going to be a multiple, again, not necessarily a constant multiple of the run, and this gives me the relationship between them. So that's switching from dx to u prime dx being du, that's essentially adjusting the bases of our rectangles in our Riemann sum and switching from a small change in x to a small change in u.